to take the derivative of something with an exponent on it, but that exponent is a variable, we cannot use these properties up here. We have to do something different. Well, we just learned that we can take the derivative of a base to an exponent that has a variable in it. And that is done in a different way than these things are. But here's the problem with this one. This is a variable and that's a variable, x to the x power. How do I take the derivative of that? Well, we can't handle a variable that's in the exponent and in the base at the same time. So we need to figure out a way to get rid of either the base or the exponent. And the way that we do that is by applying natural log to both sides. As soon as I do that, I can rewrite this as the natural log of y equals x times the natural log of x. Now I can take that derivative. How do I take that derivative? Product rule on the right. Implicit differentiation on the left, because we're taking the derivative with respect to x. So what is the derivative of the natural log of y with respect to x? So dy over dx can be written as y prime, right? So 1 over y times y prime, which is just y prime over y. Like u prime over u. Other side, we got to use the product rule. So what do we get? The derivative of x is 1, so we get the natural log of x plus 1 over x times x, which is just x over x, which is 1. So now we have y prime over y equals the natural log of x plus 1. Multiply y to both sides because we need an answer that says just y prime equals. So now I have y times the natural log of x plus 1. That's not a very good answer though. What is y? X to the x. So now I have y prime equals x to the x times the natural log of x plus 1. There's your answer.
I had an x in there.
So altogether, not too difficult of a derivative once you realize that you have a variable to a variable, and then there's a different way that we have to handle that.
Sure, that's a good idea.
Exponential functions applications include compounded interest. You've seen these problems ever since Algebra 1. Now we're going to apply them in calculus. The Algebra 1 way does work just fine. Well, then here you go. We're living in Algebra 1 right now. For compound interest problems, the general formula is A equals P times 1 plus R over N to the nth power. A is the balance at the end of the year. P is the initial deposit. It's called the principal. That's why the letter P is used. The initial deposit into the account. Or the initial amount into the account when time is 0. 1 is 1, obviously. R is the interest rate expressed as a decimal. N is the number of times that the interest is compounded, monthly, yearly, quarterly, weekly, daily, continuously, things like that. And then N in the exponent is the same as the N down here. I need a T here. Pretty sure there should be a T there. Yeah, there is. Can't we just plug it into Excel? No. To get the formula for interest that's compounded continuously. So up here we have compounded whatever, monthly, daily, weekly, hourly, not continuously. The formula for compound interest that's continuous is derived from this situation right here. The limit as x approaches infinity of 1 plus 1 over x to the x power is the same as the limit as x approaches infinity of x plus 1 over x to the x power. That all is the same as just saying e. So take my word for it. These things right here are the same as the number e. Using this definition and letting n approach infinity in the above formula, we wind up with that formula right there. There should be a t here. Apparently I was not liking my t's. Nice. A equals p e to the rt. There has to be time in there, otherwise you don't know how much interest you get. So this is compounded continuously. This is compounded some other amount per year. If we let t, oh, sorry, there shouldn't be a t here. This is for 1 year. If we let t be the number of time in years, and that's why I don't have a t here. Maybe if I actually prepared for class ahead of time, I would remember I don't need a t there and I don't need a t there because I'm talking about just 1 year. In those cases, time is 1. So the t kind of like disappears. But now if we let t be any amount of time in years, then we do get this t here and the t in that one. So my apologies. Compounded n times per year, compounded continuously. Which one's the best? Well, the answer is it depends, because you like interest, but so do credit card companies. You like interest to be compounded as much as possible. But if you are in debt to a credit card company, then you want interest compounded as little as possible. The difference isn't much, but over time it adds up. So some practice with that. A deposit of $2,500 is made to an account that pays an annual interest rate of 5%. If you find an account that does that these days, that's probably a pretty good account to invest in, and I'd put in way more than $2,500, just letting you know. Find the balance in the account at the end of 5 years if the interest is compounded quarterly, monthly, and continuously. So pretty straightforward problem. For quarterly, we're using the equation A equals P times 1 plus R over N to the NT power. For continuously, we're using the equation, what? PERT. P equals A equals PERT. P e to the RT power. PERT plus. That's a shampoo. So for quarterly, we're going to write A equals what? 2,500 times 1 plus. The rate is 5%, but that makes over compounded quarterly, so over 4 to the 4 times 5 years. You type all that into your calculator and get an answer. Yeah? Okay. $3,205.09. Okay. Pretty good. What about compounded monthly? What does my equation turn into? Compounded monthly, there's 12 months in a year, so to the 12 times 5. The nice thing is on your calculator, you can just recycle the equation you just used, change the 4 to a 12 in both cases, press enter, what do you get? $3,208.40. What's better, $3 more or nothing? $3 more is better. And how about continuously? What's my equation for continuous? E to the So what is it? Okay, so clearly compounding continuously is the best option. Obviously, in this case, with only $2,500 initial deposit, you're not making that much more money. But over time, this one starts to take off much faster than these two do. If you had a much larger initial deposit, this one would take off much faster than these two do, and these differences in money would quickly become much greater. Now the other thing is, this E came from the definition that we had here. What happened is we wound up taking the limit as n went to infinity. The number of times being compounded went to infinity. This whole thing then turned into E. And that's how we wound up with this E sitting right here. All right, so that's the math. That's the calculus behind what allows us to do a continuous compounding. All right. That's how you do problems like this. Now let's make it more fun. How long will it take for the initial deposit to double if interest is compounded quarterly, monthly, and continuously? So if the initial deposit doubles, then how much will I have? $5,000. So I'm going to wipe this because I don't have space. And we'll go up here to quarterly. And we want the population to double, or the population. It doesn't matter actually, but in this case it's money. 5,000 equals 2,500 times 0.05, which is 4 to the 4t, because we want how long. We don't know how long, so t is our variable here. So there's a couple of things we can do before we really have to do something.
I told him Excel can do this.
We have to solve for t. So we can divide both sides by 2,500, and we can simplify this here. So divide both sides by 2,500, and what do we get on the left? 2 equals, what does this turn into right here?
4.05.
No. It's probably more like 1.0125
Yeah, 1.1.
to the 4t. Now if I'm trying to solve for t, then what am I going to do? Take the natural log of both sides. Because that allows me to take this exponent and write it out front, and then I can solve for t. So now I have the natural log of 2 equals 4, wow, this thing's not writing. Wow. 4t times the natural log of 1.0125. So now to solve for t, what do we need to do? Divide by 4 times the natural log of. Because that will leave me with just t.
Then we get
To both sides.
4 natural log of 2 minus 9.
Type it into your calculator, and you get t equals your answer. Natural log of 2 divided by 4, natural log 1.0125. 13.95. 94 what? 9494. So actually that would be 13.949 if I'm going to 3 decimal places. Fish. Years. So there's your answer. For quarterly. So let's go ahead and do monthly and continuously. Go ahead. For monthly, it's 13 point, what was it, 8? 8918, so 892. And then did we do continuously yet? So for monthly, all you had to do was change the 4 to a 12 and the 4 to a 12, but that changes this number right here. That's what you forgot to do probably.
Can you just figure out
For continuously, I'm going to write the 5,000 again equals the 2,500. But this is e to the 0.05 t. So now I need to take the natural log of both sides still after I divide both sides by the 2,500. This becomes a 2. I take the natural log of both sides. The natural log e of e to the 0.05 t. This disappears, and now I have the natural log of 2 equals 0.05 t. So I can divide. And I get t equals something. 13.863. And these are all years. So that should make sense. If this one is gaining money the fastest, then this one should take the least amount of time. Notice that 13.863 is really not even 1 day more or longer or shorter than this one right here. And then this one is not really that much less than that one. And we kind of knew that was going to be the case, considering after 5 years, it had only increased by like an extra $10 or something. So not that much difference, but it's a difference nonetheless. And that's why the more you compound per year, it benefits you if this is your interest. It benefits banks and creditors if this is not your interest, if this is their interest. So you always want to find the interest and compounding that's going to benefit you the most. Either more compounding per year for your interest or less compounding per year if it's your debt. Okay, another application of exponential growth is bacterial cultures. Yeah, there's lots of science in math, and there's lots of math in science. And this is one beautiful example of, there's actually lots of math in zombie apocalypse too. But anyway, bacterial culture is growing according to something called the logistics growth function. The logistics growth function, yeah, it's a legitimate thing. And you can apply it to lots of things in nature. Lots of natural occurrences follow this sort of routine. And we'll talk about it once we get done with this problem. So, here is your logistics growth function. This is just being given to you. There is a way for this to be derived, but we don't know it yet. So, just take for a given that this is actually true. Y is the weight of the culture in grams. T is the time in hours. Find the weight of the culture after 0 hours. Okay, well that one should be relatively easy, right? That's like the initial weight of the culture. So what do we do? Plug in 0 for T. I think it would depend on the situation. You'll see what I'm talking about once we get through the problem. So we have, plug in 0 for T. So we have Y equals 1.25 over 1 plus 0.25, and then what happens here? E to the 0 is 1. So that's 0.25 times 1, which is just 0.25. So we simplify that, and we get 1.25 over 1.25, which is 1. So, weight of the culture in grams, so that's 1 gram. 1 G. Or you could think of that as like 100% of what we started with, or something like that, okay? There is a way for you to have, you've been given a problem that asks for percentages. That would be like 100% in that case. Okay. After 1 hour, what do? We plug in 1 where we see T, so we have Y equals 1.25 over 1 plus 0.25 e to the negative 0.4 times 1. Calculator. 1.0705, so 1.071 G. The nice thing is for 10 hours, pretty easy switch. Y equals still the same thing. What do we get? Okay, and what about infinite hours? No. This takes logic. Look at the equation that you're given, and I want t to go to infinity. If t goes to infinity, what happens to this part of the denominator? Does it?
E raised to any equivalent
Uh-huh.
times a constant, so infinity does come to infinity plus
You've left off one small detail.
the negative.
The negative exponent here makes this number, yes, when I have an infinity in here, this does make infinity, but it's negative. When e goes to negative infinity, what happens? It goes to 0. Because what we really have here is 1 over e to the infinity power. So it becomes basically nothing. This disappears, so I'm left with 1.25 divided by 1, which is 1.25 grams. So based on this, it will never get bigger than that. Bacterial growth follows the logistics growth function in a closed system. Why would that be?
Because it grows to, like, it grows to its meter.
There's a limiting capacity in closed systems. Like bacterial growth in a petri dish.
Yeah, it can't.
If it's closed, it can't outgrow the petri dish. It has only what is given to it inside that petri dish to grow. Therefore, the amount of growth and death must reach some sort of equilibrium so that that bacteria can continue to function. The equilibrium point here is 1.25 grams. It will never grow beyond that. And there's stuff all over the place in nature and in our lives that follows this sort of pattern. So it's called the logistics growth curve. If you were to graph that, clearly, you would think that the bacteria would pretty much go like that, right? But what happens is the bacterial growth gets to a point where, yeah, the conditions were great for exponential growth here, but eventually the system that that stuff is in can't keep up with that rate of growth. So that rate of growth starts to decrease. And eventually it gets to a place where it just can't go any farther unless something in the system changes. Maybe temperature or food supply or the volume or something. Something has to give in order for that, whatever it is, bacteria, plant life, wildlife, to go past that situation. Okay? So it's a very fascinating phenomenon, and it does occur all over the place. It's very real. Where is this 1.25? Where did that come from? That's not a coincidence.
I knew something was up.
So if you think about it, in the infinite time frame, if this term disappears and that 1 is sitting there, then we're always going to wind up with the numerator divided by 1 to give us that number. This dotted line right here would be where on the y-axis? Yeah, 1.25. So there's a lot of math that goes on here beyond what we did here, but we'll get into the logistics growth curve a little bit more probably later on, but it is definitely a very real phenomenon.